Good day, class, and welcome back to our Calculus 1 class. So we are going to be looking at linear approximation and differentials. Last time we studied how we can derive the equation of a tangent line. Say, for example, if we have this curve and we find this tangent line. Okay, let me make it. So say we have some curve like this, and we can have our tangent line this way. Now we say at this point, say A. So we can find the equation of that tangent line to the curve. So we want to use that idea. If you look at this, what we are saying is that we want to use this straight line to approximate this curve. So let's say this is y equals to f of x. And let's say this is equation of a straight line. I will just call this y equals to mx. So we want to use this y equals to mx to approximate this curve. Now, guys, look at this. You would notice that at this point, x equals to a. Any point that is closer, very close. Say, for example, if our a is 2, numerically, say 2.1. The curve will still be very close to this point that we have here. So we say we can use that equation of the straight line to approximate that curve at points that are very close to our A. I hope that makes sense. Now, using that, we remember that to find the equation of the tangent line, we use this formula, y equals to f of a, that particular x equals to a, right? Plus the slope there, that's a, then multiplied by x minus a. We already know this. We have learned this in past class. Now, since we want to use that equation of the tangent line to approximate our curve, so we just label it L of x. That is linearization of our function f of x at x equals to a. And then we have this formula. So it is just using the formula you already know. And then conclusively, we say our function, that is the curve itself, will be approximately equal, not exactly equal, but will be approximately equal to L of x. And this is called the linearization of our curve f at A. Now we claim that near point x equals to a, just like I showed you the other time, like if a is 2.1, the function and its tangent line have almost the same value. Why do we care to do this? Well, it helps us to approximate numbers quickly. It helps us to estimate function values without a calculator. It helps us to simplify complicated functions. This is very, very important. It helps us to simplify complicated functions. And it is a start to a very big concept in math called Newton's method being used in numerical analysis. Let us use example. All right. Now, find the linear approximation of f of x equals to square root of x. Let us then you use your solution to approximate the square root of 4.1 using linearization at a equals to 4. So let me make this better so that you will understand what is going on here. Okay. At a equals to 4. So I'll put it that way. Okay. All right. Now, let us find a linear approximation to that function. Well, Very simple, as we have said. We know that if we can find that linear function, then we can say it is approximately equal to our f of x. That is our target. And we know that L of x equals to f of, what is our a? At a equals to 4. So f of 4, maybe for the first time, let me write the formula. F of a plus the derivative of that f at a multiplied by x minus a. Meaning we need to find, so I will say that our a equals to 4. So we need to find f of a, which is f of 4. And that is square root of 4, which is 2. We need that. Now we need to compute the derivative. Let us first find the derivative. Remember that square root of x is the same thing as x raised to power 1 half. So if I take derivative of that, I have 1 half x raised to power negative 1 half. That is, I need to bring this down, then subtract 1 from this to get the derivative. Having done that, then I can rewrite this as 1 over 2 square root of x. That is just from indices. Now, that implies that the derivative of f at 4, or at a, which is the derivative of f at 4, will be 1 over 2 square root of 4. So which is 1 over 2 times 2, which is 4. So we have that. Therefore, our L of x, I can say my f of x, which is approximately equal to L of x, now is equal to, what do I have? Is equal to f of 4 plus, uh, plus f prime at 4, then x minus 4. So which is f of 4 is, we find it to be 2 plus f prime of 4, we'll find it to be this, then x minus 4. So this is the linear function that linearizes our square root function at x equals to 4. You can still keep, expanding these, but there is no need for that. So we have our linear function, which is this. Okay, now we want to use it to approximate 4.1, square root of 4.1. Now, let us see how we can answer that. I will call this part A, I'll call this part B. So we want to compute the square root of 4.1. I can rewrite this as, let's see. Let's see. So I can say now, I'm looking for this. Remember that the linearization of our square root function is 2 plus 1/4 of x minus 4. Now, in this case, our x is 4.1. So what is L at 4.1? Then I can use, what I'm claiming now is that I have converted my square root function to this linear function. I hope that makes sense. That is what we did in this part. We are saying we have approximated that square root function to this linear function. So we can just use it straight up. So which is equal to 2 plus 1/4, then 4.1 minus 4. So which is 2 plus 1/4, 0.1, and that is 2 plus, that is 0.2, then in 20, 4 in 0, 0, 0.4 in 1, 0, then in 10, 2, then in 20, 5. So, and that is equal to 2.025. So our claim is that, remember it is an approximation. So our claim is that square root of 4.1, square root of 4.1 is approximately equal to 2.025. That is our answer. Now let us check from calculator. From calculator, what is the square root of 4.1? So do that and compare your answer with what we have here. Let me see what's square root of 4.1. Okay, here I'm having 2.02485 and so on. So look at what we have. 0.0248, which I can approximate to 2.025. Look at what we have from the linear function that we use to approximate our square root function. So that is the beauty of calculus. You can see it helps us to find that to find solution to square root of 4.1. Okay, approximate e raised to power 0.1 using linearization at a equals to 0. In this case, we were not given a function, but we can make something up. So we can say let f of x be equal to e to the x. So in that case, we are saying x is 0.1. So now, I will come back to that. So we formed this function. Now, so we want to linearize f of x equals to e to the x at a equals to 0. Again, let us do the same thing. I will take derivative of f prime of x. Derivative of e to the x is e to the x. So, now let us compute f of 0. That is e to the 0, which is 1. Then f prime of 0 is e to the 0 because derivative here is also e to the x, so which is 1. Now the linearization is, so that is f of, we will say f of 0, that is our a, f prime at 0, then x minus 0. So we have f of 0 is 1 plus 1 times x minus 0, I believe. Yes, so that is 1 plus x. So that is the linear approximation of e to the x at a equals to 0. Now, now that we know the function that linearizes e to the x, so we can compute L of 0.1 now, right? This. Okay, so which is 1 plus 0.1, and it is 1.1. Answer. Again, we can know the actual value if you go to your calculator and just type this in your calculator. Let me do one more so you can keep doing it as we continue. If raised to 0.1. So I have 1.0517 and so on. So I will just say approximately this. So which is 1.01. So see, it is the same. So we use a linear function to get the value of exponential value because we were able to linearize the exponential function at x at a equals to 0. Okay. Now, another example, we want to find the linear approximation of f of x equals to sine of x at x equals to pi over 3. And we need to use it to approximate this. Let us see what we can do as well. Still the same thing. We will do the same thing. So here we were given our function. So f of x is sine of x. So we do the same thing. The derivative of f is cosine of x. So f of our x or our a at, it doesn't matter. So let me change this to a. So at x equals 2 or at a equals to pi over 3, so we have sine of pi over 3. So from unit circle, sine of pi over 3. Remember, you have it this way. Okay, so that is pi over 3. Okay, that's too rough. From our unit circle, we have something like this. So this is pi over 3. So now, the terminal points, we have 1/2 and we have root 3 over 2. So since it is sine, that is root 3 over 2. Okay, f prime of pi over 3 is, let us see. So that is cosine of pi over 3. So which is the x component of this, and it is 1/2. Now we can write our linearization of that function. So that is L of x is now approximately equal to, remember, f of a plus f prime of a x minus a. So which is the same as f of pi over 3 plus f prime of pi over 3 into x minus pi over 3. So this is root 3 over 2 plus 1/2 into x minus pi over 3. So this is the linear function that linearizes sine of x at x equals to pi over 3 or equals to pi over 3. Now, we want to use it to evaluate. So now, to find sine of 62 degrees. 62 degrees. The first thing I need to be careful, I need to convert 62 degrees to radian angle. So, which is, so I can say sine 62 degree, let me say this. 62 degrees equals to 62 pi over 180 degrees in radian. I hope you still remember how to convert from degree to radian. If you have forgotten, just remember this. So you can say pi is to 180 degree as radian. Radian angle is to oh sorry, that is, can say degree is to 180 degrees. That was what I wanted to write, as radian is to pi. So if you just remember this relation. So in this case, we wanted to convert 62 degrees. So just do this, replace degree with 62. So in radians, you will have 62 pi over 180. Yes, so that is the value in radian. Now, I can use this to solve. Now that I know the value in radian, now I can use my linear function now to find sine. to find sine of 62 degrees. So meaning L of 62 pi over 180 equals to root 3 over 2 plus 1 over 2 times our x now is 62 pi over 180 minus pi over 3. So just leave it this way because it will be a lot, you know, trying to solve this, but it is fine this way because we can use computer to finish it up. But if you still want to, keep going, yeah, you can keep going. Just multiply, let's see. So I can multiply, let's see, we can multiply. So that is root 3 over 2 plus 1/2 into 62 pi over 180 minus, I can say that is 60 pi over 180. So which is root 3 over 2 plus 1 over 2 into 2 pi over 180, I think. So that is root 3 over 2 plus pi over 180. So which is so root 3 divided by 2 plus pi over 180. So I would just say, just leave your answer this way too, because we are not using calculator in the class. So it's fine. It's fine this way. But to check if what we have done is right, so I will continue from here just to tell you that we have a good, we have a very good idea with this linearization. So even if you stop here in exam, if you stop, for example, here, I'm fine. That is good. But for the sake of knowledge, let us see. So root 3 over 2 plus what is pi divided by 180. So I have 0.01745 and so on. Root 3 over 2 should be 0.8660. Let me check. Root 3 over 2. Okay. Root 3 divided by 2. Yes, 0.8660. So if I add this to it, 5. So if I add that, that is 0.01745. So I have 0.8835. So what you can do now is take your calculator and just go straight up to sine 62. But remember that 62 is in degrees, so make sure your calculator is in degrees. So sine 62 degrees, I have the actual value is 0.882947. So look at it. I have 8835, 8829. So you can see that is very, very close. That is very, very close. Now, you would see that, but teacher, there is some error there. Yes, there is a little bit. That is why we call it approximation. So there will be a little bit of error, kind of. And another thing we need to think of is, let me show you something before we actually leave this. Let us go back to the square root concept. Let us use our linear function that we derive for square root of x. Let us use it to evaluate square root of 5 and see something. So remember that our linearization for square root of x is this. So let us use it to find the square root of 5. So that is 2 plus 1/4 times 5 minus 4, which is 2 plus 1/4 times 1. So that is 2 plus 0.25. 0, then in 32 in 25. Yes, so that is 2.25. Now let us go to calculator. What is the square root of 5? What is square root of 5? Square root of 5. Square root of 5 is actually 2.236. So that is like 2.24. Here we have 2.25. I'm like, okay, there is error. There is error, right? There is error. When we find 4.1, our error was not that much because this is 2.025. Here is 2.025 because I approximate this, then I have 2.025. But here I have 2.236. If I approximate that, I have 2.24, which is quite large of a difference to this. That means if I say, okay, let's find the square root of, let us use it to find the square root of 6. Then we will have 2 plus 1/4, 6 minus 4. So that is 2 plus 1/4 of 2. So that is 2 plus 1/2, 0.5. So that is 2.5. Now let us find what is the square root of 6. 2.45. 2.45. We have 2.449. So which is approximately 2.45. Here 2.5. It is still close, but we can see now that there is error. There is error. The error is increasing as we are getting farther and farther away from that 4. Our error is increasing. Now you can see what happens if, oh shit. So what happens if we use it to approximate, to find the square root of, let's say, 10. So let us use it to find the square root of 10. Let us use it to find the square root of 10. That is our linear approximation of root of x. If we use it to find square root of 10, what do we have? So we have 2 plus 1/4 of 10 minus 4. So that is 2 plus 1/4 times 6. So that is 2 plus 3 over 2. That is 2 plus 1/2. So that is 3.5. What is square root of 10? Square root of 10, 3.16. 3.1622. Look at this. Look at this. Then you would see that the error is becoming bigger and bigger as we are moving farther away from these points. So you can see the percentage error is increasing as we are moving further. So that is why we say we can use it to approximate points that are very, very close, near that our A. But we see it is still very useful. It is still very useful. 3.1622, 3.5. So it is still very useful, just that the error is increasing. So we've done some examples, including trig, exponentials, and a squared root. So you can pause this video, find the linear approximation for f of x equals to cosine of x at x equals to pi over 2. In fact, Uh, I can say use your results. Use your results to find uh say cosine of use it to find cosine of let's say 93 degrees. 93 degrees. Okay. So that's a good exercise for you. All right. Now, introduction to differentials. The other time we'll see that, well, as we compute, we are getting some errors as we move larger and larger. So there is a change in our y values as well as we have small change in x value, right? So we want to study this idea using what we call differentials. Now, if I say y equals to f of x, then I can say dy dx is f prime of x. Then I can say dy, write something like this, f prime of x times dx. Now, that is where I derive this. So we say the differential of x is this dx, which is a small change in x. And the differential of y is this dy, which we can write this way. Now, this is the linear approximation of the change in our y value, the change in that y value. So we call this the estimated change in y value. Delta x is the actual change in y value, which we all know we define this way, the actual change. So we are saying now that, again, we are using this to approximate the actual change in y. That is, we are using this formula to approximate the actual change in y. So the meaning, dx, small change in x, dy, our estimated change in y or predicted change in y using tangent line. And then delta y is the actual change in y on the curve. Let us see an example. We say the length of a square is measured as x equals to 10 centimeter, but may have an error of dx equals to 0.1 centimeter. Estimate the error in area. That is not bad. Now you see, estimate the error in the area. That area is our y value, right? So let us estimate the error we could have in this situation. We know we are dealing with a square, so we can say let x represent the length of the square. Like this. So we say this is x, 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 x. So, okay, we know that the area which depends on x is x squared, right? Now we can say dA dx is 2x. So which implies that the change in area will be approximately equal to 2x dx from differential. Now, let us find our change in area now. So this is equal to 2 times our x. The length of the square is 10 centimeters. So 10 times, then change in x, that is, the error in length is 0.1. So 0.1. So that is 20 times 0.1. which is 2. So the unit is squared centimeter. So that is the error in the area. That is the estimated error in the area. Estimated error in the area. Okay. All right. That is not bad. These. Use differentials to approximate. Use differentials to approximate square root of 9.2. Square root of 9.2. So now how do we approximate this? So remember that if our function is square root of x, right? Square root of x. So we are saying that the f is approximately equal to the derivative of f, then multiplied by dx. That is what we are saying, right? So like we did earlier, f prime of x is 1 over 2 squared root of x. So which is, we can say 1 over 2 squared root of our x in this case. Our x in this case, I will claim, remember I can write this as 9 plus 0.2. So I'll claim my x is 9. Then I will consider that dx as 0.2. So which is 1 over 2 times 3 multiplied by 0.2. So which is 1 over 6 times 2 over 10. So which is 1, 3. So that is 1 over 30. So that is, what do we have here? df, the change, right? The change in f is this. Now, what is the value of square root of 9.2? So that is 9.2 is, we can say that is 3 plus we expect this change in our y value. So that is 3.130. So 1 over 30 is 0.0, then in 100, 3. So 0.033. So that is what we have. You can say this is approximately this. And if you put that in your calculator, you should get something very close to this. Okay. Let us look at this example. A sphere has a radius which is 5 centimeter. Radius of sphere is 5 centimeter, but measured with an error of, we know the error of dr equals to 0.02 centimeter. Now we want to estimate the error in volume. You need to know the volume of sphere. We used this in class last time. So volume of sphere is 4/3 pi r cubed. So dV equals to 4/3 times, let me say pi, then times 3r squared, then d. You remember? Or let me just do this. And say dVdr is that, then dV is approximately 4 pi r squared dr. Or you can just always use this. dy is approximately equal to f prime of x dx. In this case, our x is r. So that is f prime of r dr, that is dy. And our y is volume. So the v is, so that is v prime of r dr. So nothing to memorize here. You just know what you are doing. Okay, so in this case, we know our dr, which is the error that we have. We know our radius to be 5, so we can know the change in the estimate of our volume, of the error in the volume. So this is 4 pi times radius is 5 squared times 0.02. So which is 4 pi times 25 times 2 over 100. So which is, for 25 times 4 is 100, so that is 2 pi. So that is 2 pi. I need to write the units cubic centimeter because it is the volume. So that is the change in volume, or the estimated error in volume, 2 pi cubic centimeter. So it is as simple as that. And maybe lastly, let me solve this. So suppose the side length of a cube is measured to be 5 centimeter. A cube, you know what a cube is? So the side length is, uh, draw a cube this way. Okay, so the side length is x, and the height is x. Okay, it's here. Okay, now so suppose the side length of a cube is measured to be 5 centimeter. We can say let the side length be x with an accuracy of 0.1 centimeter. Suppose the side length of a cube is measured to be 5 centimeter with an accuracy of 0.1 centimeter. So use differentials to estimate the error in the computed volume of the cube. Okay, this is still similar to what we just solved earlier, but here we say with an accuracy of 0.1, which means sometimes when I give you graph and I say maybe what is the value of something, but you cannot give it. You know, some of you will give maybe, let's say I give you something like this, 2, 3, and I have a graph like this, and I say, or a graph like this, and I say you should estimate, this. Then some people will say 2.5. Some people will say, well, this is 2.4. Some people will say 2.6, right? So that is the situation we are having here. It has an accuracy. Then when I'm grading, I will say, well, the answer may be 2.4 plus or minus 0.1. So meaning if you are saying your answer is 2.5, you still get it. If you are saying your answer is 2.3, I still give it to you, right? In fact, I can say this. So meaning if you have range of value from 2.4, 2.5, 2.6, I will say it is fine. Or 2.4 or 2.3 or 2.2, I will say it is still fine. So that is what we mean by accuracy. You are giving a range. All right. Now that you understand that in this context, how do we use that here? So suppose the side length of a cube is measured to be 5 centimeters with accuracy of 0.1. Use differentials to estimate the error in the computed volume. Well, maybe I can do this. Let us first say volume of cube is x cube. So I will have that dvdx is 3x squared, and which implies that change in volume is approximately equal to 3x squared dx. Now, what do we need to do? So what we are saying is that with accuracy, with accuracy of 0.1 centimeter, it turns out that we have that our dx will be between negative 0.1 centimeter and positive 0.1 centimeter. So meaning we are taking that range. That is what it will mean with that word accuracy of 0.1 centimeter. With that being said, then I can find the v that falls in that range, right? So meaning we can do, so for the v, it means we can do 3x squared. Our dx in this case would be negative 0.1. So we have this estimated volume, change in volume, or error in volume, 3x squared 0.1. I hope that makes sense. So which implies that we have 3. What is our x? Our x is 5 centimeters. So squared times negative 0.1. So that is our change in volume. We also be having, a range. That is what it means. Just like I used the grading to explain earlier. So 3 times 5 squared, 0.1. So this implies we have 3 times 25, 75. So that is 75 times 1 over 10 negative. So that is negative 7.5 less than equals to the v less than equals to 7.5. So that is what we expect for the error in volume of the cube. So that is part A answered. Part B, compute the volume of the cube if the side length is 4.9 centimeter and 5.1 centimeter to compare the estimated error with the actual potential error. Oh, okay. Compute the volume of the cube. Okay, let us. So we measure the volume of the cube to be 5 centimeter, right? So we want to compute the volume of the cube if the side length is 4.9 centimeter and 5.1 centimeter. Let us do it one after the other. So since we measured the length as 5 centimeter. So V of 5 is 5 raised to power 3. So which is 125 cubic centimeter. So what is V of 4.9? That is 4.9 cube. And V of 5.1 is 5.1 cube. I'm just using this formula for volume of a cube. So, so 4.9 cube, that is 117.8 649 cubic centimeter, and 5.1 cubed 132.651 cubic centimeter. Now, since this is what I have, then I can compare that to these two. So that means I will be having 117.649 minus 125. So let us see the actual change in volume. Remember, this is what we use to denote the actual change, the actual error or change in volume, delta V. So the other one, 132.651 minus 125. So this is 125. So here we have 7.651, the actual change in volume. So here we have negative, let's see, 117.649 minus 125. So that is negative 7.351. So this is the actual, without using calculus. So we see this is the actual change in volume that we have. Look at the range that we have when we use calculus. So it's pretty close. It's pretty close from negative 7.5 to 7.5. Here is 7.351 to 7.6. So, guys, that is where I'm going to be stopping for this video. And so that is our work on linear approximation and differential. So you can pause this video and use it to, solve this, try it number 2. So some takeaways: linear approximation gives an approximation of the function itself, where we started. F of x is approximately equal to L of x. We use it to approximate, that is this, f of a plus f prime of a times x minus a. So we use it to approximate the function itself. Differentials give an approximation for how the function's value changes. So that is the change in the y value. So, which is f prime of x times dx. So we are this. And both of them rely on tangent line idea. So, guys, this is the end of this video. Please work on the try to be sure that you practice the concepts. See you in the next video. Bye-bye.